Hi everyone. Today's class is about the physical and mechanical properties of dental materials. We know that for the proper selection of a dental material, we need to know its exact properties and peculiarities. To understand that, we need to know the physical and mechanical properties of dental materials. So this lecture is an outline about the various physical and mechanical properties of dental materials. What are physical properties? Physical properties are based on the laws of mechanics, acoustics, optics, thermodynamics, electricity, magnetism, radiation, atomic structure, or nuclear phenomena, according to Anisevi's 11th edition. So basically, physical properties are those properties which defines the nature of a material on in terms of laws of mechanics, acoustics, optics, thermodynamics, electricity, magnetism, radiation, its atomic structure, or nuclear phenomena. Not all these features are important in a dental perspective, but uh, in dental perspective, certain physical properties and certain mechanical properties and of course optical properties plays a very important role. By saying that the hue, value, chroma, and translucency are physical properties that are the laws of optics, for example, which is the science that deals with phenomena of light, vision, and sight. Whereas thermal conductivity and coefficient of thermal expansion are physical properties that are based on the laws of thermodynamics. So all these laws plays an important factor in determining the property of a material, and which also helps us to select the appropriate dental material for its designated use. And what is mechanical properties? Mechanical properties are measured responses, both elastic and plastic, of materials under an applied force, distribution of forces, or pressure. Mechanical properties is otherwise defined as it is a subset of physical properties that are defined by laws of mechanics as physical science that deals with energy and forces and their effects on bodies. So now let's see a brief overview of materials which is used in dental. All the materials used in the dentistry can be broadly divided into metals, ceramics, composites, and polymers. Metals, as we know, we are familiar with metals, which the main important property of metal is that in its atomic level or molecular level is that they diffusely share valence electrons among all of the atoms in solid and have specific properties. So this is an important feature of metal, which makes it highly thermal conductive and also electrically conductive. This is the main feature of metal, and also this feature helps in its all other properties like malleability, ductility, etc. Its luster, etc. So metals are basically a bunch of atoms or atomic cores with a surrounding sea of electrons. But ceramics is a contrast. It is a chemical mixture of metallic and non-metallic elements, which is does not have any particular order of arrangement. So its properties also depends upon that. Whereas composites, these are physical mixtures of blends of metals, ceramics, and other polymers. So composite is entirely a different category, which is different from both metal and ceramics. And polymers, on the other hand, is another special material which is made up of long molecules composed principally of non-metallic elements that are chemically covalently bonded. So any material which has an atomic structure and it has also a subatomic structure, and on the higher end it is having a lattice composition, and lattice composition has certain defects, and there is bonding between molecules. This is the basic structure of every molecule or substance which is present in the entire universe. Coming to the basic classification of materials, we know that matter exists in three main forms, that is solid, liquid, and gas. Solids has lowest kinetic internal energy and maximum molecular attraction, whereas liquids have high average internal kinetic energy and average molecular attraction, so that the molecules are in continuous motion. Whereas gases has a maximum internal kinetic energy and minimum molecular attraction, so that it does not have a definite shape, or it occupies a large volume. And there is also a material can transform into among these basic states, that is a solid. When it undergo melting, it turn into liquid. On the opposite, when it freezes, it becomes a solid again. And liquid can evaporate to form gas, and the gas can condensate and form liquid. On the other hand, a solid can directly undergo sublimation and form gas, and gas can undergo deposition and form a solid. And there are atoms exist in the form of molecules. And molecules even attract each other by different interatomic bonds. So the basically the interatomic bonds can be divided into primary and secondary. The primary forces are those which make the molecules by itself, and secondary bonds are bonds which is made up of which is seen in between two molecules. So force holding atoms together are known as interatomic bonds, and these forces can be divided into primary and secondary. And interatomic primary bonds is again divided into ionic bonds, covalent bonds, and metallic bonds. Ionic bonds are simple chemical type resulting from the mutual attraction of positive and negative charges. And the classic example is sodium chloride, that is, sodium loses an electron and chlorine attains an electron. Whereas covalent bonds in many chemical compounds, two valence electrons are shared by two adjacent atoms. For example, the hydrogen atom, which is its typical characteristics of covalent bond is that the typical direction of orientation. So in case of hydrogen atom, electron is shared by two hydrogen cores. Metallic bonds, on the other hand, is free valent electron which can easily donate and are able to move freely in metal space lattice to form the electron clouds. The electrostatic attraction between these electron clouds and the positive ions in this lattice provides the force that bonds the metal atoms together as solids. The ability to conduct heat and electricity is due to so-called free electron present in the metals, and also their deformability is credited to the slip of atoms along crystal plates. Example, pure gold metallic structure. So this is a diagram which represents these basic three primary interatomic bonds. The first picture is that of a sodium chloride atom. The sodium loses an electron, and the chlorine gains that atom, and a strong ionic bond is created. Whereas metallic force bonding, we have a sea of electrons surrounding positive cores. Whereas in a hydrogen atom, where a covalent bond exists, an electron is shared between two hydrogen atoms. And there are certain other bonds which exist in between molecules, that is the interatomic secondary bonds. One of the important interatomic secondary bond is the hydrogen bond, which exists in water. Can be studied, this hydrogen bonds can be studied using water molecule. Here, covalent bonds exist between oxygen and hydrogen atom, which share electrons. As a consequence, the protons of hydrogen atom pointing out from the oxygen atom are not shielded efficiently by the electrons, and thus the proton side of the water molecule is positive charged. On the opposite side of the water molecule, the electron that fills the outer orbit of the oxygen atom provides a negative charge, and therefore a permanent dipole exists that represents an asymmetric molecule. The hydrogen bond, which is associated with positive charge of hydrogen caused by polarization, is an example of this type of secondary bonding. And there is other secondary force, intermolecular forces, which is known as the van der Waals forces. In an asymmetric atom, the electronic field constantly fluctuates and a dipole is formed. Normally, the electrons of the atoms are distributed equally around the nucleus and produce an electrostatic field around an atom. However, this field may fluctuate so that a charge becomes momentarily positive or negative, attracting other similar dipoles. Such forces are quite weak. Crystal structure. The attraction between atoms make them approach to the minimum equilibrium distance during solidification. They arrange themselves in crystalline ordered manner so that each atom is positioned symmetrically with neighboring atoms to have minimum energies. Bravius has shown that there can be 14 varieties of networks of lattice points so that each point has identical surrounding. So these are the 14 possible lattice forms, that is simple cubic, body-centered cubic, face-centered cubic, simple orthorhombic, base-centered orthorhombic, body-centered orthorhombic, face-centered orthorhombic, simple triclinic, rhombohedral, hexagonal, simple monoclinic, base-centered monoclinic, simple tetragonal, and body-centered tetragonal. Among these 14, some of the only few are very commonly seen. That is, these three basic crystal lattice structures are the most commonly encountered crystal lattice structures. So the most common varieties belong to the cubic system, that is face-centered cubic or the FCC. They have one atom at the center of each face in addition to those at the corners. For example, uh, gold, silver, copper, platinum, palladium, aluminum, lead, iron, etc. has face-centered cubic lattice. That is, a central there is a as each face has an atom, and so all at the corners, the atoms is shared by four sides. And simple cubic system or SCC has 8 atoms positioned at the corners of the cube, for example, sodium chloride. And body-centered cubic structure has have one extra atom at the center of the cube in addition to those at the corners, for example, sodium, potassium, lithium, iron, chromium, etc. Come into the physical properties of dental materials. So far we saw the general properties and principles of dental materials. Now we come into the core of the subject, that is physical properties of dental materials. The first thing which we need to discuss is the abrasion and wear resistance. Hardness has often been used to indicate the ability of a material to resist abrasion. We know that oral cavity, it is not a static place. It is constantly subjected to different types of forces, which may include masticatory forces, forces or the contacts that occur during speech or parafunction, etc. So there is a variety of, always there is force existing in the oral cavity which the tooth withstand. So hardness is a very desirable property or a very crucial property of a dental material which is used to replace the functionality of a tooth. And the application of hardness is the wear of enamel by ceramic and other restorative materials spelling out. The hardness of the material is only one of many factors that affect the wear of enamel surfaces. We cannot control the biting force of the patient, but we can polish the abrading ceramic surface to reduce the rate of destructive enamel wear. You know that ceramic crowns are given to replace lost crown structure. So ceramic has better hardness or more abrasion resistant than the enamel. So if we provide enamel, ceramic crown over enamel, by the time the enamel will be upgraded by the ceramic. But what we will do to prevent this, we will polish the ceramic surface so that the effect of abrasion is reduced. So the property of abrasion resistance depends upon several factors like the hardness, the biting force, uh, the chewing frequency, uh, the diet abrasiveness, intraoral liquids, temperature changes, surface roughness, surface irregularities, etc. Where is the loss of material that is characterized by oral cavity by the loss of the original anatomical form of the material? Occurs from both physiological and pathological conditions, usually undesirable in the oral cavity, but can be highly beneficial during finishing and polishing. Another important physical property is the rheology, which is the study of flow characteristics of materials. For liquids, flow is measured by viscosity. For solid, considers the property of rheology is it is studied under the headings of creep or viscoelasticity. Certain solids also possess certain flow characters. For example, glass is usually known as a supercooled liquid. So it is also shows certain flow characteristics. So certain features are explained under the category of creep and viscoelasticity. First, we will discuss what is viscosity. Viscosity is the shear stress divided by shear strain rate. For example, imagine a laminar flow of a liquid. So the liquids flow in planes. If you imagine it as different planes, the viscosity is the shear stress divided by shear strain applied by each plane on the plane which is located adjacent below. On the basis of viscosity and how it is affected by shear stress or shear rate, liquids can be classified as Newtonian, pseudoplastic, dielectric, plastic, and thixotropic. Newtonian liquids are those liquids whose viscosity is independent of shear rate. This means such liquids have constant viscosity. Uh, uh, on the graph, it is similar to a straight line. So this include examples like water, freshly mixed zinc phosphate cement. Pseudoplastic shear thinning liquids, they show a decrease in viscosity with an increase in strain rate until it reaches near constant value. Examples include the polycarboxylate cement and silicone impression materials, where shear thinning makes the fluid flow from syringe much easier than it would otherwise have been. The third is a dilatant or shear thickening liquids, which show an increase in viscosity with an increase in shear rate. Examples are traditional conventional resin composite and also fluid resin denture based material which solidifies under pressure. Another category is the plastic liquid. They are rigid until a certain yield stress is applied to them and then attain constant viscosity. The application of this yield stress cause flow in a plastic material is called the Ingham characteristics. For example, is a non-dental example is a ketchup. Fifth material is thixotrophic liquid. Fluids become less viscous and more fluid under repeated application pressure, which is referred to as thixotrophic. This type of behavior occurs when there is some molecular rearrangement caused by the mixing and lack of time for the molecules to return to their normal arrangement before mixing again. The effect of this is that the longer the fluid is mixed at given shear rate, the lower the shear stress and hence the viscosity will be. If the fluid were left for long enough, it would recover and the whole process would be repeated. The examples are dental prophylaxis paste, plaster of Paris, resin cements, and some impression materials. The exotrophic property of impression materials does not allow them to flow out of tray before seating it. Coming to the flow characteristics of solid substances or supercooled liquids, which is characterized as creep and flow. Creep is defined as a time-dependent plastic strain of a material under static load or constant stresses. There are two types of creep, that is static creep, time-dependent deformation produced in a completely set solid subjected to a constant stress. And there is dynamic creep, the first phenomena when applied stress is fluctuating, such as fatigue type of test. Metal creep usually occurs as the temperature approaches within the 100 degrees Celsius of the melting range. The most important example is the dental amalgam. Because of the low melting range, dental amalgam can slowly creep from a restored tooth site under periodic sustained stress. Creep rate has been found to correlate with marginal breakdown. Thus, the higher the creep, the greater will be the marginal breakdown. According to ADA specification number 1, it is advisable to select an alloy with creep rate below 3%. The term flow rather than creep is generally being used in dentistry to describe the rheology of amorphous materials such as waxes. The flow of wax is a measure of its potential to deform under a small static load, even that associated with its own mass. Usually, compression is used to test creep or flow. To measure the flow and creep, a cylinder of prescribed dimensions is subjected to a given compressive stress for a specific time and temperature. The creep of our flow is measured as the percentage of shortening in length. Coming to other important physical property, that is color and color perception. Color is a result of physical modification of light by colorings as observed by the human eye and interpreted by the brain. Color is again defined as color is the sensation resulting from stimulation of the retina of the eye by the light waves of certain lengths. So, coming to the nature of the light, color cannot be perceived without light, which is a form of electromagnetic energy visible to eye. The visible part of the spectrum comprises electromagnetic radiation falling between wavelengths of 380 to 780 nanometer. The visible spectral range is called for polychromatic light. White light can be separated into monochromatic components if it passes through prism or diffraction bars. If the wavelength of the electromagnetic radiation is less than 380 nanometer, it is called ultraviolet radiation. And if it exceeds 780 nanometer, it is called infrared radiation. This is an example of white light that is going into the prism and it is dividing into its constituent with geo spectrum. Light reflected from the object is brought to the observer's eye. Light enters through the optical system and the image is focused into the retina. The retina is a complex mosaic of millions of nerve endings which transforms the light stimulation into a nerve signal that is further transported to the brain. So, color of an object is perceived when direct light falls upon the object. It is either absorbed, reflected, or transmitted. If all the light is reflected, the object appears white. If the light is entirely absorbed, the object appears black. The larger the amount of light reflected by the object, the brighter the object will appear. Furthermore, the greater the intensity of the direct light source, the brighter the object will appear. The final effect depends greatly on whether the object is transparent, translucent, or opaque. At low levels of light, the roles of human eye are more dominant than the tones and color perception is lost. As the brightness becomes more intense, color appears to change. This effect is known as Bezold-Brooke effect. That is, depending upon the brightness, the color perception of the same object varies. And in order to understand color, the color is divided into various dimensions. To accurately describe our perception of a beam of light reflected from a tooth or respiration surface, three variables must be measured. So the color can be described in three dimensions, the color space measured as hue, value, and chroma. The hue describes the dominant color of an object, refers to dominant wavelength present in the spectral distribution. In Munson's words, it is the quality by which we distinguish one color family from another. The order of the physical hue is Vibgyor, that is violet, indigo, blue, green, yellow, orange, and red. But within the visible spectrum, there is no clear demarcation between these distinct lines. The primary source of natural tooth color is dentin, and its hue is either in the yellow or yellowed or orange. Value, in other hand, is the relative blackness or whiteness of color. On a scale of black to white, white has high value, black has low value, and midway between the black and white is medium gray. Value is the quality by which we distinguish a light color from dark. Value is the only dimension of color that can exist by itself. Value differences are more noticeable and thus have more relative significance in the dental restoration than hue or color. Finally, the third component, that is chroma, is the dimensional color that defines the intensity or concentration or degree of saturation of hue. In Munson's words, it is the quality by which we distinguish a strong color from a weaker one. Pale colors have low chroma, whereas intense colors have high chroma. In teeth, it is dictated by the dentin and influenced by the translucency and thickness of the enamel. And for measuring the color, there are several systems, one of which is known as the Munson's color coordinate system. So light pale colors are towards the top of the cylinder and dark colors are towards the bottom. That is, the value is arranged on a vertical level. The hub of each wheel represents a value axis. The hues are arranged sequentially around the rim. The spokes represent the gradations of the chroma from the colors axis to the purest hues at the rim. Another important feature that determines the color perception is the property of metamerism. The change in color matching of two objects under different light sources is known as metamerism. This is because they have different color reflectance curves. Standardization of illuminance in color matching diminishes the effect of metamerism. So in order to color match a tooth, we need to have certain standardization for the lighting of the dental operator. Another important feature is the fluorescence. Fluorescence is the emission of luminous energy by a material when a beam of light is shone on it. Some human teeth emit fluorescent light when excited by ultraviolet radiation, that is 365 nanometer. The fluorescence being polychromatic with the greatest intensity in the blue region, that is 450 nanometer. This property contributes to the vital appearance of the teeth. It primarily occurs in dentin because higher amount of organic material is present. Clinically, the operatory or dental lab color selection is usually done by use of shade guides. This type of shade guides are available, which is matched with the natural tooth in order to come into the identification of the proper color of the tooth. That's all about the optical properties of dental materials. Coming to the thermophysical properties. The first important property is the thermal conductivity. The thermal conductivity of a substance is the quantity of the heat in calories per second that passes through a specimen 1 centimeter thick, having a cross-sectional area of 1 centimeter square, when the temperature difference between the surfaces perpendicular to the heat flow of the specimen is 1 Kelvin. Its unit is watts per meter per second per Kelvin. Materials with high conductivity are known as conductors, and with low conductivity are known as insulators. For example, a large gold or amalgam filling or crown that is in proximity to the pulp may cause the patient considerable discomfort as a result of temperature changes produced by hot or cold foods and beverages, unless adequate tooth tissue remains or non-metallic substances are placed between the tooth and filling for insulation. Such failing materials are, as cements are relatively poor conductors and insulate the pulp in this area. So this is a chart which shows the thermal conductivity of different materials, which is generally used in dental dentistry as compared to normal structures like enamel and dentin. Here, obviously, the metals will have a higher thermal conductivity, and non-metals like composite porcelain have less thermal conductivity, almost similar to that of enamel and dentin. And another important feature that is comes in close relation to thermal conductivity is the linear coefficient of thermal expansion. The linear coefficient of thermal expansion is defined as the change in length per unit length of the original length of the material when the temperature is raised by 1 Kelvin. This results in gross expansion of the material. SI units of linear coefficient of thermal expansion is expressed in micrometer per millimeter degree rise in Kelvin, or ppm per degree Kelvin. When coefficient of thermal expansion of a respiratory material and tooth structure are different, they expand and contract to different degrees as temperature change. This promotes leakage at the interface between them. A relationship exists between coefficient of thermal expansion and melting point. Materials with low melting point exhibit large coefficient of thermal expansion. This is a chart which explains the coefficient of thermal expansion of inlay waxes, silicon materials like and polysulfide impression materials, mercury, composite resins, and metal restorations like amalgam, gold, and non-metals like porcelain, etc. Coming into the mechanical properties of dental materials. Mechanical properties are defined as a subset of physical properties that are based on the laws of mechanics. Mechanical properties are defined by the laws of mechanics as physical science that deals with energy and forces and their effect on bodies. All mechanical properties are measures of resistance of a material to deformation or fracture under an applied force. The normal of forces ranges from 200 to 3,500 Newton. Adults in the first and second molar area it is 400 to 800 Newton, and the bicuspid and cuspid incisor areas it is 300, 200, and 150 Newton respectively. And forces on respiration. The study of forces in natural emission include forces and stresses on respiration such as intracoronal respiration, single multiple unit fixed restorations, RPT, and complete tensions. Coming into an important mechanical parameter, that is stress. Stress is defined as a force per unit cross-sectional area, or F divided by A. Its unit is Pascal. And there are different types of stresses, that is tensile stress, compressive stress, shear stress, and fractional stress. Tensile stress is caused by load that tend to stretch or elongate a body. It is always accompanied by tensile strain. And compressive stress is defined as internal resistance of a body under a load that tends to compress or shorten it, associated with compressive strain. And shear stress tends to resist the sliding or twisting of one body over the other. And flexural stress is the bending forces in dental appliances. These are the examples wherein a compressive stress and tension comes in hand by hand in a FPD. In the cantilever FPD, the tension and compression switches its position. So it depends upon the type and form of the restoration. This is a diagram that represents the different forces or stresses that can occur on dental material. Strain, on the other hand, is a change in length or deformation per unit length when a material is subjected to force. Strain is equal to deformation divided by length. It is dimensionless, easier to visualize. It can be elastic strain and plastic strain. Elastic strain is reversible, whereas plastic strain is permanent deformation. And when we plot the stress and strain on a graph on X and Y axis, it gives the stress strain curve. It characterizes the mechanical properties of a material obtained using mechanical testing machine, which is example is Instron. The strain is plotted over x-axis, an independent variable, and stress is plotted over y-axis, and curve obtained in comparison, tension and shear stress. If stress is increased, strain is also increased. It is linear relationship between stress and strain is up to the proportional limit. Further increase can result in to reach the material to reach into fracture point. Stress corresponding to T is the fracture stress, and corresponding to E is the yield stress. By this, we'll end today's presentation. So far we discussed about the various physical and mechanical properties, and we will continue or continue other mechanical properties in our next lecture. The other mechanical properties will follow in the next lecture.